Four-pole electric motor, explanation and function by David C. Johnson. What we have here are Maxwell's equations. Alright? These are equations that have to do with circuits and electronics. And it's the second equation, that is Gauss's law of magnetism, and the fourth equation, Ampere-Maxwell law, that we're going to be taking a look at. For the case of our motor, that is. Alright, if we take a look at the very top, alright, if I can squeeze that in here. Alright, what we're going to see that the closed integral of B dot ds, that is the integral of the field around the loop itself, is going to be equal to mu naught I. Mu naught is the permeability factor, and I is the current. So this is basically saying Ampere's law, any current carrying conductor also produces a magnetic field, B. Well, the net B field is directed downward here in this picture. So what we have is these little loops, alright, and each of those loops represents current, with the current, the magnetic field, the B field, at that particular point around that current carrying conductor. And the net field is pointing downward, and that's going to be important as we're going to see later on. The important thing is that it's pointed downward. Alright? What we have to our left, alright, is a solenoid, or a number of those coils, right? And notice that we have many loops. If the current conductor has many loops, or a coil, the magnetic field B is concentrated in the middle of the coil. Lines of flux can be seen. That is, phi is equal to the integral of B dot dA. So notice if we have a lot of coils, you're going to have a strong magnetic field. That is, going to have a strong magnetic field, in this case directed upward. This is that same coil, alright? But as you can see, in terms of geometry, the electromagnet that we have created here produces the B field seen. Because of the number of coils that is in, the strength of the B field can be calculated, alright? So the field itself, as we can see, goes up the middle of the coil where it's concentrated, and toward the outside where it tails off. Right, this is actually on both sides of the coil. Notice there's a north and there's a south, as you would have in all cases for magnets. There's always a north and the south. Alright? Now, using Ampere's law, what we're going to do is take the closed integral of B dot ds is equal to, in the end, mu naught n over L times I. That is to say, the number of loops here, the number of loops contributes to that magnetic field, as I said before, and this is mathematical proof of that. There's a path to this, though. If we would take this cross-section of this coil and direct it toward path 1, 2, 3, and 4, we can forget about 2 and 4 because they're what? Perpendicular to the coil. 3 is on the outside, so we don't care about that. It's only path 1 that contributes to the internal B field that we're interested in. Alright, and this funny looking thing down here, alright, actually that's going to be on my next slide. And we're going to see that there's a phi, alright, there's a variable called phi for the flux line. Now, what happens if we take these poles here, if we take the magnet, electromagnet, and we form a wheel with it? All right, we call that a rotor. The rotor is literally a wheel whose metallic ferromagnetic spokes or coils forming electromagnets. All right, so we have electromagnet forming this spoke of the wheel, electromagnet forming that spoke of the wheel. All right, the more coils and internal area to the coils, the stronger the magnetic field be. All right, this is going to be important in just a moment, as we're going to see, because we have to power those coils. Electricity gets to the pole coils via contacts and brushes. The contacts are the little strips along the rotor. The brushes are these metal strips sitting on the outside. All right. The contacts are on the rotor while the brushes are connected to DC power source or a battery. So these brushes on the outside come into contact with the contacts themselves, and there's a contact on this side and a contact on the other side. That completes the circuit when they touch the brush, as we're going to see. All right, let's talk. That talked about the rotor. Then we're going to talk about the stator. The stator is slabs of magnets. And what are these slabs of magnets? Permanent magnets are magnetized solid pieces of metal made up of domains, which are tiny internal magnets inside of the metal itself. All right. So there are tiny little magnets inside of this magnet. Notice there's a north pole and there's a south pole. Well, each of the tiny magnets on the inside are lined up, and that's the most important thing to say. For a magnetized material, a ferromagnetic material, the domains inside are lined up. All right, the domains are little tiny magnets. So what we're going to do with these slabs, we're going to put these slabs, all right, outside, on the outside of the rotor, because we're going to see on the device itself. Stator magnets are make up the stator. These magnets provide an external magnetic field that pushes against the rotor. Electromagnets produce locomotion. All right. So what we have here is a rotor of electromagnets on the inside, made of coils. We have the permanent magnet sitting on the outside. All right. When the external field pushes on the coils, the electromagnets internal to it, then we get locomotion. All right. The Lorentz force interaction. All right. So remember, we have an external field formed by the external magnets. We have, this is an individual coil here, but remember what we said, what accompanies a coil is a magnetic field. Notice this magnetic field from the external stator points up. This magnetic field from the rotor points down, from the rotor coil points down. A current carrying conductor produces a magnetic field. Put the two fields, the stator and the rotor, in the same place, and the opposing force is produced. This is called the Lorentz force. And that's what this equation is. Force is equal to current times length times magnetic field B. All right, why am I doing this? I'm doing this project because I graduated from Xavier University twice. All right, different years. I got a bachelor's degree in physics and a master's degree in education. Then from Kansas State University, I graduated. I got a master's degree in physics there. I attended the University of New Orleans in electrical engineering. All right, and I worked at WLAE and WWL in New Orleans as well. And I'm currently enrolled at ISU, Illinois State University, seeking a scholarship. Seeking a scholarship. You want to see it work? Well, I'm about to show you this working right now. But I want you to look at my future concerns, all right? The next stages. I want to put remote control circuitry in here for starting it up. And then I have some practical applications. I've used this as a lifter. I'm going to use it as a conveyor belt for locomotion, conveyor belt. And then thirdly, I want to use, I'll make, a car, a remote control car, or a bike, by being able to put the motor on the bike itself. Or any suggestions that you have. All right? So you want to see it work? Here we go. All right, let's see if we get something here. And there you have it. And those are the principles of science at work right there. All right? If you want to contact me through Facebook or Twitter. Thank you.